Hello everybody. So this is, I guess, your review for Friday's quiz. We're going to try and get it all done as quickly as possible. So, we're dealing with mainly a couple of equations. One of them is mv, and the other is f times t, and the third is conservation momentum. So this should be pretty quick. Bernice, whose mass is 70 kilograms, leaves a ski jump with a velocity of 21 meters per second. What's Bernie's momentum? We remember the equation for momentum is mass times velocity. So the mass is 70 kigs and the velocity is 21 meters per second. So we should end up multiplying those two and getting 1470 kilogram meters per second. So that's number one. Two, Ethel is sitting on a park bench feeding pigeons when a child's ball rolls towards her across the grass. Ethel returns the ball to the child by hitting it with her 2-kilogram pocketbook with a speed of 20 meters per second. If the impact lasts for 0.4 seconds, with what force did Ethel hit the ball? So we're going to have to use this, which is giving her an impulse. So we've got time and force causing a speed change of 20 meters per second with a 2-kilogram pocketbook. So we're going to go with F delta T equals m delta v. So we're solving for the force. We know the time was 0.4 seconds equals the mass, which was 2 kilograms, and the speed, the change in velocity, was 20 meters per second. It doesn't really say that there's a start and a finishing speed, but we can assume that if it was a pocketbook, it was probably not moving. So we can say the final velocity is 20. And there's your change in velocity. So if you do that, you would divide both sides by 0.4. Divide that by 0.4. So that would cancel, and you'd end up with F equals 2 times 20 divided by 0.4, which is 100 newtons. Next, number 3, when Reggie steps up to the plate and hits a 0.15 kilogram fastball traveling at 36 meters per second, the impact caused the ball to leave the bat with a velocity of 45 meters per second in the opposite direction. The impact lasted for 0.002 seconds. With what force does Reggie exert on the ball? So the big thing here is, once again, we've got, this always happens. Keep the current color scheme. We've got m delta v equals f delta t. So we're dealing with an impulse causing a change in momentum. But this is the big important part, because we've got something going one way at 45 meters per second and something going the other way at 36. So it comes in going at 36 meters per second, and then he hits it and it goes that way at 45 meters per second. And anytime you're going to figure out the change in velocity, it's the final minus the initial. So the final is 45, and let's say that's to the left. So negative 45 minus the initial, which is 36, which is going to give us a change in velocity of negative 45 minus 36 is, and that's going to give us negative 81. And again, with momentum, the change in velocity, it's more scalar than a vector, so we can change that to a positive. But you care about the change, which is 81 meters per second in velocity. Everything else is pretty plug and chug, so 0.15 kilograms times the change in velocity, which was 81 meters per second, equals the force, which we're solving for, times the time, which is 0.002. And if you can math, to quote Mr. Diamond, you even math, bro? You're going to divide both sides by 0.002. 0.002 divided by 0.002. Those will cancel. So F is going to be 0.15 times 81 divided by 0.002. And that should give you 6,075 newtons. Calculate that. That's that. Astronaut Pam Melroy, history's third woman space shuttle pilot, flew the space shuttle Discovery to the International Space Station to complete construction in October 2000. To undock from the space station, pilot Melroy released the hooks holding the two spacecraft together, and the 68,000 kilogram shuttle pushed away from the space station with the aid of 4 large springs. If this 73,000 kilogram space shuttle moved back with a speed of a half a meter per second, how fast and what direction did the space shuttle move? So we got two things, and this is essentially an explosion problem, which is what I was trying to explain to you the other day. And forgive my awful artistic ability, but here's the space station, there's the space shuttle. In the beginning, they're not moving. I mean, they're moving, they're going in orbit, but compared to each other, they're really not moving. So our velocity is going to be 0. And after they separate, we're going to have the space station going this way, and we're going to have the space shuttle going that way. And we know the velocity of one of them because we say, well, the 73,000 kilogram space shuttle moved back at a speed of a half meter per second. So we know this thing, and the velocity is 0.5 meters per second. So we want to know what this thing is doing. And we know the masses too. So this thing is 73,000 kilograms, and we know this thing is 68,000 kilograms. And the big deal is we need to remember that the momentum initial equals momentum final. And what that is to say is whatever the momentum was here when the velocity was 0 is exactly what the momentum has to be here. Even though these things are both moving, their velocity has to add up to be, you guessed it, 0. So if we do this, we can kind of look at this a couple of ways. It's basically an explosion. You have, you can imagine a rock sitting somewhere. You stick a piece of dynamite in the middle of it, and it blows up. And this piece goes that way, and this piece goes the other way. But to start with, the momentum was 0. So what's the mass of this whole thing? Well, it's 73,000 plus 68,000. And I did that, and it is 141, hello, 10, 10, 10, Sorry about that. That was a minor technical detail. So we're dealing with, 141,000. Let's get my pen going again. 141,000 kilograms, and that's just 73,000 plus 68,000 times the velocity is 0. And that's going to have to equal the total momentum prime, the momentum after we get through this. So 73,000 kilograms times the new velocity, which is negative 0.5 meters per second. And it's negative because it's going backwards. Plus the velocity of the space shuttle, which we don't know, times the mass of the space shuttle, which we do know. So that's 68,000 kilograms times v. And now, big question here, what's this times 0? 0 equals 73,000 times negative 0.5 plus 68,000 times v. And now we're going to take this 73,000 divided times a half, or negative a half, and we can actually bring that over to the other side. And I can do that on the calculator pretty quickly. 73,000 times 0.5. We would end up with 36,500. So 0 equals 36,500 negative plus 68,000 times v. And how do we get rid of this? We're going to add it to both sides. So 36,500 equals 68,000 v. And if you notice, we're adding, because this is negative, you're adding it to both sides. So you end up with a positive 36,500 on this side, so your v is going to end up being positive. And that's important because the space shuttle goes to the right and the space station goes to the left. So right is positive, and actually if you do your signage right, you should end up with positive numbers, meaning going one way. So we're going to divide both sides by 68,000, divide by 68,000, and you should end up with v equals 0.536 meters per second, which is good. So 0.536 meters per second is the velocity, and then for part B, they want to know what they call the relative velocities are. Well, if I've got 0.536 going this way, and I've got 0.5 for the space station going the other way, well, what's going on here is what's the difference between the two, and the difference is 1.036 meters per second. So if I'm standing in the space station looking at the space shuttle, because we're both going away from each other, it looks like the space shuttle is going away at 1.036 meters per second, even though it's really going 0.536 meters per second. Because I'm moving backwards, it looks like it's going faster. So then we move on to 8. Tyrell throws his 0.2 kilogram football and knocks over his mom's 0.8 kilogram vase. I actually don't care about B, or B, so don't worry about that. But what we've got here is a football hitting a vase. After collision, the football bounces straight back with a speed of 3.9 meters per second, while the vase is moving forward at 2.6 meters per second. How fast did Tyrell throw the football? Remember, momentum initial has to equal momentum final, and it's everything involved. So the momentum of the vase plus the momentum of the football has to be conserved. So the momentum of the football is 0.2, and we don't know what it was originally doing. But we do know what the vase was doing, and that's 0.8, and the vase, I hope, it was sitting on a table, so 0.8 times 0. And we know what was going on after the collision because it tells us the football, which has a mass of 0.2 kilograms, moves backwards, negative, with a speed of 3.9 meters per second. So negative 3.9, plus this, what's going on with the vase? Well, the vase is moving forward 2.6, so 0.8, which is the mass of the vase, times 2.6. So we're going to multiply 0.2 times negative 3.9, and we're going to add it to 0.8 times 2.6. We are going to end up with, let's see, 0.2 times negative 3.9 plus 0.8 times 2.6, and we will end up with 1.3 on this side. And now we got to say, well, 0.8 times 0 is 0, so it's really 0.2 times the velocity of the football is going to give us 1.3 kilogram meters per second. So we're going to divide both sides by 0.2. We're going to end up with a velocity for the football of 6.5 meters per second. And this is kind of cool because if you know what's going on after a collision, you can always figure out what was going on before the collision. And what this means is, well, this was where that B is. So 0.2, the football is moving at 6.5 meters per second. It hit the vase, which had no meters per second, and afterwards the football bounced backwards 3.9 meters per second, and the vase bounced forwards 2.6 meters per second. So momentum is a pretty useful tool to figure a lot of this stuff out. Next up, a 300 kilogram motorboat is turned off as it approaches dock and coasts in towards the dock at a half meter per second. Isaac, whose mass is 62 kilograms, jumps off the front of the boat with a speed of 3 meters per second relative to the boat. What is the velocity of the boat after Isaac jumps? So again, it's sort of like it's another sort of explosion problem, except now you've got a rock that's not sitting on a table. It's kind of a rock with a stick of dynamite in it that's actually moving. So we got a boat, and we got Isaac on it, and the boat's moving this way, and then Isaac jumps this way, and the boat, if Isaac jumps this way, the boat should slow down or it should move backwards. So we'll see what happens to it. But we know that the boat and Isaac have a mass of 362 kilograms because the boat's 300 and Isaac's 62. And they're both moving along with a speed of a half a meter per second. And that's going to have to equal whatever goes on after this. So we know that Isaac is coming off, and Isaac is moving at, let's see, his mass is 62, and he jumps off the front of the boat with a speed of 3 meters per second, plus whatever the boat's doing. Well, the boat's got a mass of 300, and we're going to figure out what its new velocity is. So this is actually a pretty easy problem. 362 times a half should give us 181 equals 62 times 3, which is 186, interesting, plus 300V. Well, in order to get 300V by itself, we've got to subtract 186 from both sides. So 181 minus 186 is negative 5 equals 300V. So somehow, some way, the 300 kilogram boat is going to have to move with some sort of velocity to make it have a momentum of negative 5 meters per second. So this thing is going to go very, very slowly backwards. Very slowly. And if you divide both sides by 300, you should end up with a velocity of 0.016 meters per second. So basically what happens, and it just so happens this way, if Isaac was less massive, this wouldn't happen. If Isaac was more massive, this wouldn't happen. If he jumped with a different speed, this wouldn't happen. But essentially, I mean, we're going so slow, you can almost say the boat stops. So he jumps off, and just by him jumping this way, the boat stops. So I hope that kind of makes sense. These are what we call sort of explosion problems, where you've got one thing turning into two things. Whereas the next problem we're going to see with a bullfighter, we're going to see two things become one thing. So we're going to have Miguel, a 72 kilogram bullfighter, and we're going to have a bull. Bull. Angry bull. There you go. Angry bull. So our bull's going this way. Miguel is going this way. So we're going to have momentum here, and then Miguel is going to jump on the bull, and then we're going to have momentum afterwards. So let's see. The momentum of Miguel is 72 times, let's see, his speed running towards an angry bull at a speed of 4 meters per second. Yep, couldn't catch me doing that for $1 million. And the 550 kilogram bull, 550, is going towards Miguel at 12 meters per second. But the bull is going that way, so that's going to be a negative 12. And these two are going to add up to the same thing as whatever's going on after the collision. And what's going to happen when Miguel jumps onto the bull? Well, we're going to add his mass to that of the bull. And we're going to have this thing is going to be running that way, whatever way it is, with a new speed. So we'll figure out what that new speed is. But to do that, we need to remember that we have to add their two masses because the two masses join. So 550 plus 72, last time I checked, is going to be 622 meters per second, kilograms times that new velocity. So if you add this all together, you should get 6312 negative equals 622V. Remember, this is negative 12 because he's going that way, and this is positive 4 because Miguel's running towards the bull. So you have a small positive with a big negative, and you add them together, you're going to get a big negative number. And then you can divide both sides by the mass of the new thing that they form, divided by 622. You should get a new velocity of, drum roll please, negative 10 meters per second, give or take. So we're going to have this thing with Miguel on the bull going that way at 10 meters per second. So I hope that helps. Next up, a space shuttle astronaut is sent to repair a defective relay in a 600 kilogram satellite that is traveling in space at 17,000 meters per second. Suppose the astronaut and his manned maneuvering unit, the MMU, have a mass of 40,000 kilograms and travel at 17,010 meters per second towards the satellite. So in reality, I mean, they're both going really fast, but the difference in speed is only 10 meters per second. So, you know, if the astronaut hits the satellite, he's not going to explode and die and blow up and stuff like that. He's only going to hit it with a speed of about 10 meters per second. What's the combined velocity of the astronaut when they grab hold of the satellite? So this is another perfect inelastic collision. We're having two entities that are going to become one entity, and we have to conserve momentum. So we've got, and I'll just do it this way, m1v1 plus m2v2 equals m1v1 plus m2v2. These are all prime. So we know the mass of the satellite is 600 kilograms, and we know the speed of the satellite is 17,000 meters per second, plus the mass of the astronaut, and his MMU have a mass of 40,000 kilograms. Is that 40,000 or 4,000? 400. 400 kilograms, sorry. Little typo there. Sorry about that. 400 point. There you go. I thought that was a very big, heavy, massive astronaut. Times their velocity at 17,010. Now, if this is a perfect inelastic collision, we're not going to have two entities here anymore. We're going to have just one thing. So we're going to have a new mass times a new velocity. And last time I checked, 600 plus 400 is going to give us 1,000 kilograms, and our new velocity is going to be what we're figuring out. So 600 times 17,000 plus 400 times 17,010 is going to give you a pretty big number, and we can figure that out. 600 times 17,000 plus 400 times 17,010. We are going to get a very, very large number, 1,700,400 equals 1,000 v divided by 1,000. Their new velocity is going to be 17,004 meters per second. So, I mean, if you're in space, and this is true, whenever the space shuttle docks with something, whatever it docks with slows down. Whenever an astronaut grabs onto something, whatever they grab onto slows down. So it's, you know, when we're talking about orbit, you have to be really careful how fast you go into orbit, and you actually, whenever these things dock, the space shuttle has to fire rockets to make it go faster because it slows down. And then when they undock, they have to fire rockets to slow it down so it doesn't go flying out of orbit. So whenever these two objects in space collide or change, you know, basically pieces fly into it or pieces fly away from it, the velocities change because momentum has to be conserved. So that's always interesting, I thought. So just to go back to it, remember the satellite was going 17,000, the astronaut was going 17,010. The astronaut slows down, the satellite speeds up. So, and that's what you end up with. Last but certainly not least, and we are on a video that is probably being really boring to you, but we are only 23 minutes into it, so if it takes a while to do your homework, sorry. USS Constitution is the oldest fully commissioned warship in the world. It is docked in Boston, Massachusetts, also known as Old Ironsides, for a seemingly impenetrable hull. The frigate houses 56 pieces of heavy artillery. Mounted on bearings that allow them to recoil at a speed of 1.3 meters per second are two carronades, which each with a mass of 1,000 kilograms. Carronade fires, and the carronade's a cannon. So if each of these fires a 14.5 kilogram cannonball straight ahead, with what muzzle? The carronade fires a 14 kilogram cannonball straight ahead. With what muzzle velocity does the cannonball leave the cannon? Alright. So here's the cannon. Here's the ball. The initial velocity of both of these is 0. So I don't care how heavy this thing is, the momentum is going to be 0. After the explosion, the cannonball goes that way, and the carronade, the cannon, goes backwards. This is our recoil. This is why whenever you shoot a gun, it pops back at you. The bullet goes one way, and because of the conservation of momentum, the gun has to go the other way. So there's a little bit of math involved here, but it really shouldn't be that terrible. Let's see here. The recoil speed, so we know the mv is 0 when it starts. And that is going to, so our momentum is 0. And that's going to end up to be m1 v1 plus m2 v2. This is of the cannon. This is of the ball. So 0, because that's our momentum to start with, and we're going to conserve it, equals cannon. What's the mass of the cannon? 1,000 kilograms. And the carronade goes backwards with a V of 1.3, because that's the recoil, plus M2, that's the mass of the cannonball, 14.5 kilograms, and we're looking for the muzzle velocity. So how fast does that thing go? So 1,000 times 1.3, last time I checked, is 1,300, plus 14.5 V. And that's going to be equal to 0. And how do we get rid of this? Well, we subtract it from both sides. So negative 13. Oh, wait. If this goes backwards, that should be negative, which means that's negative. And when we add it to both sides, we have positive 1,300 kilograms equals 14.5 V. And then we divide both sides by 14.5. 14.5. Your velocity of your cannonball is 89 meters per second. Positive. So the ball goes positive, the carronade goes backwards. So there you go. I hope this helped, and I hope seniors especially, you watch this and you appreciate that this is the last thing you're going to learn in physics.